Okay, let's jump in now into a slightly harder problem. So honestly, I say harder, but it's really just that it takes a few more steps. A bit more involved. But you can do this, I believe in you. So, what are we looking at? Well, we have a compound shaft drive that has several pulleys on it. And it's shown right here in this figure. Segments 1 and 2 of the compound shaft are hollow aluminum with a shear modulus of 4,000 KSI. And they have an outside diameter of 3 inches and a wall thickness of 0.125 inch. Segments 3 and 4 are solid, and they're 1/2 inch diameter steel with a 12,000 KSI shear modulus. And all our bearings allow things to move perfectly freely because no friction in this world. What do you want to know? Well, you want to know the maximum shear stress in this compound shaft. You want to know what the rotation angle is of flange C with respect to pulley A. So this guy right here and this guy right here. And we determine the rotation angle of pulley E with respect to pulley A. So how far is this one turning with respect to this? Okay, so with all of that in mind, off with you. Go try it out. See what you get. And if you need help, I'll be here to help you. So, try it on your own. Grab your rubber duck, grab your traveling gnome, grab your little piggy bank. I'm picking things on my desk. And try out the problem. So, I will see you all soon. 3, 2, 1, and we're back. Let's try it out together. Okay, first off, let's write our equilibrium equations, okay? Gotta figure out equilibrium equations. Let me see if I can get some. There you go. So, if we do our symmetry on the x-axis, what we're going to find is that our torque in section 4 is going to be 95 pound-foot. And if we go to our section 3, we'll find that torque there is negative 175 pound-foot. In our first section, our torque will be 650 pound-foot. And our internal torque in sections 2 and 3 will be the same, so it would be negative 175 pound-foot, because there's no torque applied in between them. Now, I think I have a picture of this on the next slide, and I do. So you can see a bit better how I'm cutting everything here. When I cut right there through segment 4, I got rid of everything to the right of it, and so I only had 95 pound-foot. Since that torque would be pointing out and to the right, that's a positive torque. In this second section, torque 3, I've got 95 pound-foot pointing left, I've got 270 pound-foot pointing right, and then I have torque 3 also going right, which obviously it's going to have to be going the opposite direction to make sure that it's going to be able to cancel out that 270 pound-foot. And that is why it's a negative torque, because torques are positive if they're pointing away. This one's pointing into it, so it's negative. And then for T1, we cut it right there, we got rid of everything to the left, and it's a positive torque because the torque is pointing out. Okay, let's go back here again. So other things we need to care about are getting our polar moment of inertia for both of those cases. Now, we have two hollow sections, that's 1 and 2, they're both hollow. And so we're going to have to use our hollow polar moment of inertia equation. Now, we know that their wall thickness is 0.125 inches, so the diameter of that hollow section is going to be 3 minus 0.125 times 2. So that is where this 2.75 is coming from. When we do that, we get that their polar moment of inertia for sections 1 and 2 are going to be 2.33740 inches to the 4th. Okay, already looked at these. Let's keep on going. Now, segments 3 and 4 are solid, so we use our regular formula, and we just plug it in, and we get that their polar moment of inertia is 0.49701 inches to the 4th. Now, what's the shear stress in each segment? Well, we have the elastic torsion formula. We know what their shear modulus is. We know what their polar moment of inertia is. And we know what the torque is. And so with that, we should be able to solve. I did my towel in the wrong direction. I feel silly. There you go. There you go. Good enough for now. So, like I said, it's not necessarily all that difficult with these equations. It's just you're doing it 4 times. Not very fun. We see that our max shear stress happens in section 1. So, that would be 5,010 psi. Okay. Now what about the angles of twist? Once again, it's just plug and chug. We already knew all of this. Just be very careful that we're converting all of our units. We had 650 pound-foot here, pound-foot. And so we're going to need to convert that to inches because everything else is in inches. Now that we've determined the angle of twist for each section, we have to figure out the angle of twist for each point. Now you're like, well, what's the difference? Well, you have to think about it. If you have a single rod and I'm twisting it, then I can say that this side doesn't move and this side does twist. Or I could say that this side doesn't move and this side does twist, or some combination of the two. So for like section 1, on the right, the hand decides at point A, and the left-hand side is point B. So if I'm saying that both of those are twisting, I've got a twist A and a twist B. Well, then the twist that I've already calculated, which is for this section, not for the individual points, would have to be the twist at B minus the twist at A. And that would just happen to be equal to this. And so we do that for each of our little sections. For section 1, 2, 3, and 4, we say that those are equal to the difference between the angles of twist of those points, their endpoints. Now this is important because we're going to be looking at everything with respect to point A. We look at the point C with respect to A. We look at the pulley E with respect to A. And so because we're doing that, well, it makes things a little bit simpler. We're going to say that the angle of twist at A, it's the origin, and so it doesn't have a twist. So with that, I can then calculate the angle of twist at B, which is simply the angle of twist in section 1. And then, now that I know the angle of twist at B, I can calculate the angle of twist at C. Now, this one is different. It is not just, well, B is now 0, so C is the angle of twist section 2. No, B has a twist because B is not our origin. A is our origin. We've gone from here to here. No. We said this was 0. Then this was 0.0601. This is point B. Now we're moving onward to point C. We're going to figure out how much with respect to point A has C turned. So in this case, we're trying to calculate point C. And so we know what the angle of twist in section 2 is, as well as the angle of twist at section in point B. And so we can solve for it. We do that, and we get that it has turned 0.052 radians. So it turned back a little bit. And then we're going to keep on continuing this process all the way along it until we get all the way to our pulley right there at point E. So at point E, with respect to A being 0, it will have turned an angle of 0.0433 radians. And it'll look something like this. So here's our torque diagram, here's our shear stress diagram, and then finally here's our angle of twist diagram, showing how it would change. Okay, so we can then pull out our answers, which are saying what's the rotation angle of flange C and the rotation angle of pulley E. We already calculated those, and here they are. So I hope this made sense. The big thing to remember is that we had to set an origin when we were doing all these to get the relationship between all the points. We could have just set A to anything, honestly, since it's always about the difference. But it made it a lot simpler just to say that it's 0. So thank you for listening, and I'll see you all next time. Bye-bye.